We are given this circuit. So initially the switch is closed. So some current will be flowing in the circuit. Now here, this battery has some internal resistance also that is given. So let me just redraw this figure so that let's include the internal resistance. So now this is the circuit, some current will be flowing through it. Across capacitor, voltage will remain constant. And then it's given that this switch is opened. So when that happens, we need to find what will be the energy of oscillation immediately after and t time after the switch is disconnected. Now for the first part, in this circuit, where is the energy stored? It's in the inductor and in the capacitor. So if you suddenly open this switch, this loop is still there. So we know the flux through L cannot change suddenly. So current will continue to flow in this inductor. And the charge on the capacitor also cannot vanish immediately. So the energy of oscillation in this circuit immediately after is same as the energy stored in capacitor and inductor when the switch was closed. So let's find that energy when the switch was closed. So at right this moment when the current is flowing, let's find what's the energy in the inductor and what's the energy in the capacitor. So that's what I have written here. So at t is equal to 0, after disconnecting the switch, current I through inductor and charge accumulated on the capacitor will not change suddenly. So energy of oscillation will be due to both, due to the charge and due to the current. So energy will be half CV square. So voltage across this capacitor will be V minus IR. And energy through inductor will be half LI square. So current in the circuit is V upon R plus R. So we'll put that value here, simplify it, and this will be our answer. So this is the energy in this LCR circuit at t is equal to 0. Now that energy will of course decrease because of the damping due to the resistance. So after t time, what will be the energy? So we know energy is of the form of half Ka square. So this amplitude can be written, so it doesn't matter what A represents. It can represent voltage, it can represent current, because all these amplitudes are proportional to each other. So we get this half K A naught e raised to power minus beta t whole square. Whatever that amplitude is, whatever quantity it represents, it will be varying by this function. So we do that, and beta we know for the circuit will now be R by 2L. So we put that, so we get some maximum energy times this. So we know maximum energy is the initial energy, that is E naught, that we already calculated. So our answer will be simply E naught e raised to power minus RT by L. So excellent problem, because here you can see energy also varies, energy amplitude is same as energy. So in other terms of current and voltage, you have that sinusoidal function also here, but energy simply decreases within exponential function, and maximum energy will be at t is equal to 0, that is E naught.